let's look at problem 820, short encoding of words. So here we are going to provide two greedy solutions. So before we share the solutions, let's make a comment. So for this kind of problem, the standard method is using prefix tree or trie. But here we feel that the greedy method itself is also of interest. So we'll share two versions of that. So first, I'll go through the statement of the problem. Then we will look at the method and the procedure. And finally, we share the code and make some remarks. So let's first look at the statement of the problem. So basically, the first big paragraph explains what's a valid encoding. So a valid encoding of an array of words is any reference string S and array of indices such that the word's length equals the index's length, and the reference string S ends with the pound character. So for each index I, the substring of S starting from indices I and up to but not including the next pound character is equal to word I. So the problem requires that given an array of words, we return the length of the shortest reference string S, possibly of any valid encoding of word. So the last part actually indicates that the shortest encoding may not unique. So this is the problem. So let's look at one example. So in this example, we have Tam and me and Bell. Then the output is 10. So here it gives a valid encoding. So similarly, we can try Bell pound plus 10 pound and change the indices accordingly. Also, this is a valid encoding. So notice in this problem, me is a suffix of time. So that's a point that's actually indicating, or we can solve this problem by prefix tree if we consider the reverse of the words. But here, what we want to share is some greedy method, which is might be also interesting, because if we would like to use the trial method, we need also to compute the root to leaf sums, right? So with that said, let's look at example 1. This one is a sort of edge case because it contains only one string, and the encoding is nothing but t plus a pound. So the constraints about this problem are as follows. So the words has length which is bounded above by 2000, and each word has length less or equal than 7. So due to this numerical constraints, so we can use a sort of brute force greedy method. And here the last one says words I consists of only lowercase letters. Okay, so with this constraint went through, let's look at the method and the procedure. So here the method we're going to use is the greedy method. So the procedure is as follows. First, we sort the words descendingly according to length, and then we actually mimic the building the encoding by traversing the word list and check if word plus the pound is in the previous state of the encoding string S. So in between, we are going to update the length of the encoding string. So let's look at example 1. So here is the word, right? So if we sort by length in the decreasing order, we have a word such like this. Or it's possible the bell comes from before time. It's okay. Then we do the iteration. So we initialize empty string S, and then currently the length of S is 0. Then for index I, what we are considering is 10 pound. So we check if 10 pound is in the current state of S, which is not. Then we update this S by adding or concatenating this 10 pound. Then the length of this s increment to 5. Then for I equals 1, so we consider bell pound. So this is not in s again, so we concatenate this part with the previous state of s, so we will get 10 pound plus bell pound. So the result increments by the length of bell pound, that is 5 again. So the result now is 10. So at index 2, so we are going to check me and pound. So this me and pound is in s because me is a suffix of 10, so we do nothing. So finally we return 10. So that's the procedure. So here actually this part may be time consuming. So if we check if word plus pound in the previous state of s. So also in the second version of the greedy method, we will use set to help a little bit in this situation. And before we do the code, let's make two remarks. First, we'll present two versions of greedy method. So we will encourage you to think of their connections or similarities. So this is remark 1. And remark 2, so the general method to solve this problem is prefix tree, also known as trie. But here we need to consider the reversed word. So you can try this method too. But in this method, we need to consider the length or from the root to the leaf and then add them together, which will be the final result. So, but for the greedy method, which we feel that it's very neat in some sense. So let's run the procedure. First, I'll do some initialization. So we will introduce the empty string s. Let's call it s. And let's initialize a result which records the length. So next, we want to do the sort. So this is the step. The sort basically O log n algorithm. So words. So what we want to do is we do sorted. So we do sort the words according to the key. So let's define a key function. So it's equals the length of w, but in a reverse fashion. So then up to now, after the sort, we can run the above procedure. So that is mimicking the procedure. So for this, basically we just need a for loop for word in words. So what we want to check actually is the current one. So if word plus this pound is in, if it's not in s in the previous state, we are going to concatenate this part with the previous state of s. So s plus equals word plus this pound. So in this process, we are going to increment the result by length word plus 1. So plus 1 means the pound. So with that said, actually we are ready to return the result. So let's check the generic case for this situation. It is passes the first one, and the second one is the sort of routine. Let's check it for safety. It passes. So let's check the generic case. Yeah, it passes the generic case. So as we remarked that here we are checking this word per pound in such a fashion. So actually we can do this by using the set abstract data structure. Let's do that. So here let me copy this part, and we call this solution v1. And then I'm going to write another solution, and hopefully it stimulates some thought about the method and their similarities. So here basically I'm going to use a greedy method again, but with the aid of a set or the abstract data structure. So for this, so this actually before we do that, let's make a comment. So the set actually essentially the set plays a similar role as the prefix tree. Let's first share this part of code. What we want to do is, again, we sort this word. So let's do sort. So copy this part. That will be sufficient. And then what we want to do is that we initialize a set just as a helper, and also a result which is originally 0. And then what we want to do is the following. So we do the for loop for word in words. What we want to do is, if we check if word in the, we just continue. So otherwise we just check the word reversely for I in range length word -1. So we're ending at 0, so we need to write -1 here with increment -1. So that is decrement by 1. So in this case, we are going to add this word from I to the end. That's actually essentially the suffix. So with that said, so after this procedure, we are going to increment the result by length word +1. So +1 actually is the same as the first method, because we need to consider the end of word, or the pound. So that's about it. So then we return the result. So here is the update, and the thirdly we just do the return. So return the result. So now let's check the generic check a special case first. Let's check for example 1. Oh yeah, it's the same. So let's check generic case. So yeah, it passes the generic case. So I guess for this problem here, we are providing a greedy method and using 2 different formats to represent this method. Essentially, they are the same. And also in example, in the second solution, so this part essentially plays the role of prefix tree. So I would encourage you to try to write a solution by using prefix tree, by considering the reverse of the word and then compute the root to leave pass sum and add them together. That will be the result corresponding to the result here. I guess that's it. Thank you very much.